Assalamu alaikum, students. So this is lecture number 9A, and today we are talking on the windings of your machine, and we are discussing DC machines up till now in this course now. I have bifurcated this lecture into 9A and 9B for the ease, so that this lecture is solely dedicated to one type of winding, which we are going to discuss today, that is a lap winding. Today I'm going to talk on the simplex lap winding, and a little bit, if time is there, then we can talk about the duplex winding also. What is duplex, simplex? We will just discuss that. Now, in the last lecture, if you remember, I showed you physically the armature and the stator or the rotor and the armature in your hands, and I showed you physically. Today I have those pictures also in my workpad sheet. So over here in this one, as you can see very closely over there, the armature or the rotor is over here, and I hope you still remember it. I told you that this is your armature laminations over here, and all these laminations are stacked together, and certainly these are those coils ends over there, and you can see each slot maybe having like more than one or two coils over there or loops over there, and all these are interconnected over here with these segments. You can see the soldering points over here. So all these coils are actually soldered here to these segments over there. Today what we are going to learn over here is this, that how this winding is done, and certainly which type of winding is done, so that then it is connected with how many commutator segments. So what I am actually looking forward over here is this, that these commutator segments, which are important over here, so that because carbon brushes are actually going to be constantly sliding on these segments, so these commutator segments are going to be calculated by the winding design, and that winding design which we are doing today is called as the lap winding over here. Now if I go towards this diagram, I didn't need to explain anything further over here, because again the same commutator bars or segments are there. How many bars or segments are there, that's a part of your design, and how these connections are done over there. You can see the ends over there, they are the ends of the loops over there, so they are like many conductors. You can count even the number of conductors over here, 1 2 3 4 5 whatever. And this is the winding coil, as I told you, or the loop. These are the carbon brushes, certainly not attached, but physically they will be attached here and here. If they are like two carbon brushes or four carbon brushes over there, this is the armature core. Again the same laminations over there. We call this one as the stacking of the teeth or slot. Now this opening over here, this is actually the slot, and these ones are called as the teeth over there, because for the obvious structure over there. Now this is the stator and the field winding, just like I showed you in the previous class. This is the field winding. It's a two-pole machine, so you have the DC machine over there. Now if you can see very closely over here, the lap winding over here is going to take its name from the word, the lap winding is actually going to take its name from the word overlap winding. Now what this means actually over here is this, that whenever you are going to show one coil, and supposedly one coil, or if you coil number 1 is going to start from supposedly slot number 1, and supposedly it is going to go up till supposedly slot number 6, for example, going towards any design. And then there is a coil number 2 that is going to have another slot started and then another slot ended over there. But for especially for the lap and overlap winding, which is actually coming on from the overlap, as the word suggests, that the two coils are overlapping each other. So when I'm talking about coil number 1, it is started from slot number 1 and ending at slot number 6. Coil number 2 may be starting from, not always, but maybe starting from maybe slot number 2 and ending at slot number 7. So what this means, that the coil which is at slot number 1 and slot number 6, you will start from slot number 1, do like many number of turns, and then complete your coil, and then you will bring your wire back at slot number 2, and then you will do whatever number of turns, and then that is the second coil completed over there. So this means that coil number 1 and coil number 2, there is going to be an overlap of those coils. So what I mean by this over here, now how you are going to represent a coil and how you are going to draw the winding diagram is actually a very important thing. Now for this purpose over here, if I can show you diagram over here. So if I'm talking about the lap winding over here, and if you are talking about, so normally in any design, whenever you are showing a winding, supposedly this is the slot number 1. Now this type of diagram which I'm drawing over here, and I'm making vertical lines. Now these vertical lines are actually made from the essence that you are going to show each vertical line as one slot over there. So this vertical lines are actually one slot. Now what I mean by this, if you see very closely this diagram, so maybe I can start my numbering from over here, and I can call this is slot number 1, this is slot number 2, this is slot number 3, then 4, and so on. Supposedly, like there are like 12 slots over there, so this is 12, this is 11, this is 10. So these are slots over there. So each slot has been marked as one number, and since you can see, we are more interested in the conductor which is placed inside this slot. So what I'm doing over here, I have marked each one of these slots over here as one name. So supposedly, if this is slot number 1, this is slot number 2, this is slot number 3, this is slot number 4, 5, 6, and 7, so on. I'm not going to complete the whole diagram. We will do it for the whole nomenclature over here. So now if I have this diagram over there, I just told you coil number 1 is going to be connected from slot number 1 to slot number 6. And it will have some number of turns per coil, that is NC over there. Now I'm not going to show that slot number 1 to 6 over here in any number of turns over there. So what I'm going to show over here is this, that from slot number 1, this wire will be connected to slot number 6 over here, and then your wire actually started from slot number 1, and this was the starting end of your coil over here. So your coil completed from 1 to 6, and then certainly it will bring back the wire from here, and then you will again do many number of turns. But I'm not going to show that number of turns over here for obvious reason, because that will make the diagram cluttered over here. So 1 from 6, this is one coil shown. So this means that from 6 now, as I just told you, I will go back to my slot number 2 and then start another coil. So what this means, that from here 2 is going to be connected with 6, and then from 2 I am going to connect it to slot number 7, and similarly this will again come back maybe over here, and then maybe it is again going to start from slot number 3. So what is happening now, as you can see, on this one I have this one as slot number 1. Slot number 1 started for the first coil, so this was my first coil, and I showed this coil as over here. So the finishing end of this coil was here, the starting end was here. So now the second coil has now started from here, and this is going to finish over here. So now this is S2, this was S1, this was F2, this is F2, not S2. So now you can see the two coils, they are overlapping each other. So when this is the case, this type of winding in which the coils are overlapping each other, this is called as lap winding. So the winding is called as lap winding. And here in this case, you can see this is slot number 1. Coil number 1. So this is starting end of that one. I can call this one as F1, and here I can also call it as S2, because the finishing end of one coil is actually the starting end of the other coil. So here in this point, and then certainly this is F2 over there, and then certainly this is also S3 over there, because they are interconnected over there. Please remember again that if coil number 1, so if this one was coil number 1 over here, this is coil number 1, and this is coil number 2. I'm not showing over here how many number of turns per coil are there. What I mean by this, so if I'm starting from 1 and I'm completing my path up till this one, practically I will go back and do many number of turns over here, maybe like 20 over here, and then complete it. But here I want to keep my diagram neat and clean, so I will just specify over here when I am specifying this one, okay, that number of turns per coil here is 20. So the designer or the manufacturer of that one will automatically know that the designer has actually told us that the number of times you are going to repeat the same coil 20 times over there. So I hope you still remember from the last lecture that Z was equal to 2C NC, where we calculated a total number of conductors, where NC was the number of turns per coil. This NC is the same number of turns per coil which I'm talking about here, that from 1 to 6 it is going to have a repeat every time over here, and then we are going to finish the coil, and then the second coil is going to start. So this type of winding in which the coils are repeating each other or overlapping each other, not repeating, sorry, repeating, overlapping each other, these are called as the lap winding over there. And if you see very closely in this one, this is also a lap winding example over there. Now the machine which I showed you in the last lecture, the physical machine, this was this machine over there. Now if you see very closely over there, these are three different views of your machine, and these three different views are telling you that supposedly, certainly this is the front end of your machine over here, because here the commutator segments are there. Similarly, this is the front end of your machine, and this one may be the back end over here. Similarly, over here, this is the back end over here. Similarly, this is the front end of your machine, and certainly this is the back end. Now, what is the meaning of word front and back? Now, front here actually means because here you are going to have a connection with your commutator segments over here. These commutator segments are going to be the front end, so you are going to have the connections of your loops over there. But if I go on the back side, which is certainly not available over there, but if I see this side, you can see coils are coming out over there, and there is going to be an interconnection. So over here, if I go back to your diagrams, if you see very closely over there, since this was the starting end over here and then the finishing end over there, but these are interconnections of the wires. So this side over here, this one, if I mark it supposingly, so this side over here, we call this one as the back end of any coil. So this is called as the back end of any coil. And this one over here, this one, we call this one as the front end of the coil. So this front end of the coil over here. And one thing very important, as you all know, that we are only interested in the conductors which are inside these slots over there, from slot number 1 to 7 or so on up till 12. Why? Because these are the ones which are actually going to produce the force, or they are actually going to produce the energy or EMF over there, so that the machine can actually be given their electrical energy if it is working as a generator, or if it's acting as a motor, then the torque is going to be created in these one. So but these white color wires which I've shown over there, they are certainly required, and you require a little bit of connections over there, because these connections are actually completing the whole current path inside your machine. So the two words over here, back end and front end. And now very important nomenclature over here. Now if you can see, I started from slot number 1 and I ended at slot number 6. This is my first coil. So overall, the span of this coil, you see this very carefully, the span of this coil over here from 1 to 6 over there, since this is a connection from the back, this is connection from the back, this over here is depicted as YB over here. That is called as the back pitch. Very importantly, pitch. As you all know, what is the word pitch used for? Pitch is certainly the distance between any of the 2 points over there. So here between slot number 1 and slot number 6, here your YB is going to be equal to certainly 6 minus 1 over here 5. Now here I am not measuring distance in terms of meters or millimeters or centimeters for obvious reasons, because I have another unit called as slots over there. I have named them as 1, 2, 3, 4, 5, 6, 7 and so on. So when I started from 6, ending at 6, starting at 1 and ending at 6, I have my YB equal to 5 over there. So I have an already easily over here that YB, that is from the back end, the two ends of the same coil are connected over there as 5 slots afterwards. So starting from 1, ending at 6. But if you now see this front end, now what is this front end? Front end means that I started from, I ended at 6 over there after, of course, many number of turns. So now here from 6, I am going back to 2. And then I'm going to start. So this connection over here from 6 to 2, which is going to provide the interconnection between coil number 1 and coil number 2, is going to be called as the front pitch over here. And this front pitch is going to be called as YF. And here in this case, now this is very important because you are going from 6 to 2 over here. So this over here is going to be 4, and for obvious reasons, because this is an overlap winding, I am going to call it with a negative sign -4, because with 6 reached already, you will have 6 minus 4 and you reach your coil slot number 2 over here. So 6 minus 4 and you reach 2, and then you start the other coil. One thing very important, all the coils, one thing very important, that all coils will have same back pitch and front pitch. This is very much important because we need to have a symmetry, because whole of this rotor is going to rotate inside whole 360 degrees inside your periphery of your stator. So this back pitch and front pitch for all the coils, it has to same. So if you're designing a machine with YB equal to 5 and a front pitch equal to -4, certainly if it's a lap winding, then all the coils will have the same symmetry. You are not going to change this front pitch and back pitch over there. So these back pitch and front pitch, they are terms in terms of number of slots. You can write them as slots also over here. If you don't even write it, no issues over there. So this 5 over here is the back pitch, because this is the connection between the two ends of your coil. And each coil over here, as you can see, if I just summarize this one, you are starting from 1 and ending at 6. So this is your coil over here. So this is one coil, this is starting end, and this is the finishing end of your coil. And then you start another coil from 2, and then you connect it with 7, and this is again the starting end and finishing end. But the two coils, they are overlapping each other. That's why it is called as a lap winding. Now, coming on to how you are actually going to design a lap winding. Now, if you see very closely in our diagrams for the machines which we have seen in the class physically, as I told you to hold them. Now, I still don't know how many number of carbon brushes, how many of commutative segments are here in this one. But now what we are going to design, we are going to design a machine, and this is the same stator over there. I hope you can easily see this diagram also. So I am now going to design a machine which has the number of slots equal to 20. So my slots, which I told you last time, the number of slots is 20. And certainly, how many number of slots? So number of coil sides. Now this is very important term again. Coil side. What I mean by coil sides over there, if you are seeing this diagram again, this is one coil. This is one coil. How many coil sides are there? Certainly 2. This one and this one. I'm not concerned with the number of conductors over there, because I'm not showing them over there by any direction. So over here, this 1 and 6, these are the coil sides over there. So inside my diagram over here, the number of coil sides, I am going to represent it, sorry, by this one, is going to be Z dash, and here this is also going to be 20. Why this is going to be 20? Because the number of layers which I am working on is equal to also 1. If this number of layers was equal to 2, then this number of coil sides would have been 20 over there. And I am designing a machine which is having a number of poles equal to 4. So my machine has 4 poles and it has 20 slots. So this is very important. And the last data which is provided to you is called as the multiplicity. And this is represented as M, and here I am taking M, and this M tells us that this is a simplex winding. If it was 2, then you will call it a duplex winding. If it was 3, you would call it a triplex winding over here. Now, what does triplex, duplex and simplex means? We will talk it just later on. But at present, this multiplicity is a very important factor. And as this winding will be made, I will tell you that how this multiplicity actually takes into control that what type of winding, simplex, duplex or triplex. Now, the one which we are designing is over here today is the simplex simplex lap winding, not wave. Wave is actually the other name of the winding type in DC machine. So I'm talking about a simplex lap winding here. So I have now S is 20, number of coil sides Z bar is 20. I have used Z bar because Z was actually the total number of conductors, and if you remember it from the last relation or last experiment, 2C and C. So this was 2C and CZ. Here this is small z over here, Z bar, that is 20. And why this is 20? Because the number of layers are still 1. So number of poles P is equal to 4. And then the first thing, now the solution of this is coming up now. The first thing you have to find out is the pole pitch. Now, we have still not defined pole pitch up till now. We have been deciding on the front pitch and the back pitch, and I told you they are measured in terms of number of slot. But you have to also find out that if there is a north pole over here, let me write it down over here. If there's north pole and there is a south pole, and if there are 12 slots over there, then certainly this means that the distance from north pole to the south pole is equal to 6 slots. And for obvious reasons, because you have a 2-pole machine supposedly and you have 12 slots, so 12 divided by 2, it means 6 slots over there. So if I go back on my diagram over here, in this diagram, if I have this pole pitch, so pole pitch is going to be represented as YP, and this YP is going to be equal to Z bar divided by P equal to, over here this is 20, and here I have 4 poles, so this is equal to 5. So pole pitch is equal to YP is equal to Z bar divided by P. Z bar is 20 here in our case, so 20 divided by 4 is equal to 5. The next thing we already know, that is back pitch. We have to find out now what is back pitch. Back pitch is equal to also the coil pitch, because these are the two ends of the same coil over there. As I just told you that this distance from slot number 1 to slot number 6, this is the coil pitch over here, and this coil pitch is defined by the back pitch of your machine, that is YB. Here in this case, in this diagram I showed you, this was 5. Now for our case, which we are designing at present, this back pitch over here will be equal to Z bar divided by P plus M. This M over here is the multiplicity, so over here if I put in over here as 20 divided by 4 plus M, so this comes out to be, so this will be 5, sorry, this will be, I have to write it down as 1 over here. So this is 1. So this will be equal to 6 over there. And the next thing, which is actually the front pitch, which is actually the connection between the two ends of the coil. So this will be equal to Z bar over P minus M. So this will be equal to 20 over 4 minus 1. So this will be equal to 4. So now when this is equal to 4, these two values we have just found out now over here. This one is 6 and this one is 4. Now one thing very important which you will learn with the practice is this, that the back pitch and the front pitch, these all values have to be odd values every time. If they come out to be even, it's not applicable. You cannot make a winding with even number of back pitch or front pitch over there. So what I will do over there, that YB and YF, this YB and YF, which are the back pitch and the front pitch, certainly you can write it over here as front pitch and this one as the back pitch over there. These one must be odd. So this is very much important. Now how you are going to make them out, because we have got an answer 6 and 4. So now there are two options, because YB and YF, we know this is coming out to be 6 and 4. So I have now one option over there. I can either make it 7, the next higher odd number, or I can make it like over here 7 and 5. Or the next option is this, I can reduce it down and make it 5 and here 3. So what I'm going to do now is totally up to you. Maybe the winding is successful by 5 and 3, or maybe the winding is successful by 7 and 5. So you have to either choose 7 and 5 or 5 or 3. So you have now two options. If I write it down, this is YB and this is YF. So YB is equal to 7 and YF is equal to 5, or this is equal to 5, and this is 3. Now whichever option suits you. Now one thing, with practice you will find out that the smaller values tend to actually give a winding. One thing very important, it's not always that the winding is going to be practically implementable, because these values, as I told you, they have to be odd. And then certainly at the end of the winding there is going to be a check also, that how this winding is going to run with carbon brushes over there. Is it practically possible or not? So now you have two options over there. Either you can go with 7 and 5 or 5 or 3. Normally, please always go for the smaller value. So over here, I am going to go with 5 and 3 over there. The lower odd has a higher probability for a better design over there. So this means I am going to select over here 5 and 3, and this 5 and 3 are going to be my YB and YF. So this means they will be the back pitch, or actually the coil pitch, which is also the name for YB, and the front pitch, which will be 3 over here. Now this is coming out as 3, but when we are going to put this one in the table, this value I am going to call it as negative, because you all know this is a lap winding, and lap winding the coils are overlapping. At present I still not talked about M, but as soon as one winding is complete, I will come back to this one and show you that how this M is actually being used over there, and what this M simplex means over there. So now what I have to do, I have to actually make a winding table. So the next thing, which is very much important over here, is the winding table, which I have to make it over here. So this winding table is actually going to tell me that which coil is connected with which one. So over here, if I put the values now, so winding table is going to have YB certainly plus 5, and YF is going to be minus 3. So this winding table has to be now made minus, because you all know I told you that this is the lap winding, which means that the coils are overlapping with each other. So YB is equal to plus 5 and YF is equal to minus 3. Now here in winding table, it's totally up to you. You have to start from any one slot. And as I told you in the last lecture, that the windings are closed, which means that one end of the winding starts from supposedly slot number 1. It has to end at also 1. So then the rotor is rotating, all the coils are being energized maybe from one end and taken up from the other end. So what I mean by this, so you are going to start from supposedly slot number 1. So here in the first table, the first vertical entry over here is this, that from slot number 1, my slot coil will start and it will go up till slot number 6. So my winding is going to start from 1 for the first coil and going to end at 6 over there. And this is going to be the first coil. So YB, the back pitch, is going to be 5, fixed for all of this machine. So slot number 1 starting and going up till slot number 6 over there. So now the first coil is now going to be connected with the second coil, so that now 6 minus 3, and then I am going to start from slot number 3. So this is my first coil over here, which is going to start from slot number 1, end at slot number 6, and go back, because this is an overlap winding or lap winding. So 6 to 3, and then now my second entry over here will start from the third slot and still keep YB equal to 5. So this will become 8 over here. So 8 again, and 8 minus 3, and you have again 5. So you can see now how this is going on. You started from 1, ended at 6, then 6 to 3, another connection, and this 6 to 3 is the same connection as I showed you over here. In my case over here, this one was equal from 6 to 2. Now since this I'm doing a very mathematical design over there, so this is going out from 6 to 3, and then from 3 another coil is starting from 3 to 8, and then from 8 it's going back to 5. Now if I complete this table, now this time I have started from 5. 5 plus 5 is equal to 10, and this 10 minus 3, I'm encircling these values, because these encircled values are going to be used to make or show the winding, just like I showed you over here in this diagram. This vertical diagrams of which vertical yellow color lines are the slots in which those conductors are placed, or the coil sides are placed over here. So this table is very much important. Now if I complete this table now very quickly, so this is now starting from 7. 7 plus 5 is equal to 12. So 7 and 12 are connected, and then from 12 I'm going to come back to slot number 9, and then from 9 I'm going to again go to up till 14. 14 slot is there. 14 minus 3 is now this time going to be equal to 11. 11 is also practically possible because this is a 20 slot machine. So this is 16 now. 11 plus 6, 5, 16. 16 minus 3, 13. 13 plus 5 over here is going to be 18. So 13 and 18 are connected, and 18 minus 3 is equal to 15. So 15 is there, and then I have the 15 plus 5 equal to 20. So this is 20, and 20 minus 3 is going to be equal to 17, and 17 plus 5 here is equal to 22. Now here the interesting thing comes over there, that 22 slot is not physically present. Why? Because this is a 20 slot machine. So what is going to happen with this 22? Now if you are talking about 22 over there, this means that you will count up till 20, and then after 20, because this is a circular slot marcation, so after 20, for 21st I will call it again slot number 1. For 22 I will again call it slot number 2. So this means practically in this over here I am going to call it 22, but practically it will be again second slot, because this is the whole symmetry over here. And then over here this will be 22 minus 3. Over here this will be equal to 19, and then over here plus 19 plus 5. So this will be equal to 24, but 24 is again still not there. So I am going to call this one as the fourth slot, and then this is 24 minus 3 is equal to 21, which is actually the first slot. So what has happened over here? I started from 1 and my ending at 1. So you can see now the whole connection over there. This is a closed winding. I started from 1, ending at 1. And how many coils are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this means 10 coils are there. And this is completely true because how many slots were there? 20. So how many coils would be there? Because number of layers is equal to 1. There will be 10 coils. So this means that in the winding table, your winding is doable up till some extent if you have got 10 coils, which are exactly true because it's a single layer winding. Your S is equal to 20. So Z bar is equal to also 20 because you have L equal to 1. That is the number of layers. And here, if you can see, you are covering each and every slot over here. If each and every slot is covered over here, this means that you have almost every slot covered and there is nothing empty over here. So these are 10 rows over here. It's a 20 slot machine. So all the rows are there. So now you have the winding table, and this winding table is going to be the basis of your next diagram, which is going to be called as the developed diagram. Now this developed diagram is going to certainly look something similar like this. Here you can see these are the slots shown over there, and these are the interconnection. And when I'm going to repeat it for like 20 slots over there, this winding diagram is going to tell you that how the carbon brushes, the commutator segments, and all that stuff is actually going to be connected over here. So now if I go back on this winding table, I have this winding table with me. So now the next thing which I have to do is a developed diagram. Now a developed diagram, why it's called a developed diagram? Because if you see very closely on this one, what I have done over here, I have like 20 slots which are physically present in my machine. And these 20 slots over here are telling me that over here, you are going to connect from 1 to some slot. As if you go back on the table, your 1 is going to be connected with 6, 6 is going to be connected with 3, and I'm going to show everything. But if you take a drawing this one on a piece of paper, you can curve this piece of paper, and all of these 20 slots are now going to be in a full cylinder, just like a physical armature when you have seen this diagram over here. So this is slot number 1, slot number 2, 3, and so on up till supposedly these are 20 slots. So what I have done in a developed diagram, this is just a winding opened in form of a two-dimensional paper, and the same developed diagram is being drawn over here. So now what I'm going to do, you can see what I have done. I have made 20 vertical lines, and I have made this small lines over here so that the winding becomes symmetrical. I'm going to give you an assignment also after maybe lecture 9B also over here. So this is very much important that from this slot number 1 to slot number 20, how many back pitches. So this is the back end of your machine, and certainly this is the front end of your machine. So any coil is going to be connected. All coil sides are going to be connected from slot number 1 to slot number 20. So now I'm going to show it with another color over there just to make it a little more appealing. So now if I go back on my table, you have slot number 1 and slot number 6 connected. So this means I'm going to now show them from 1 to 6 over here. So first of all, this is very important that I make a small point over here. So this one is going to be my slot number 1 up till slot number 6 over here, like this. So this is my connection, and I started from 1 certainly, and but from 6 I have to return back to, if I go back on the table, I have to return back to 3. So this means from 6 to 3, I'm just making a center over there so that my diagram is a little legible, and this is my 6 to 3 connection over there. And certainly my 1 is going to have a winding start from here. So this is my starting end of my winding, and certainly I will have to complete my winding up till this slot number 1 again. So 1 to 6, this is coil number 1. From 6 to 2, I have gone back over here. Sorry, this is not 2. I have to went to over here for 3 over here. Sorry, I have done this mistake. So this is 6 to, so I have this 6 to 3 over here. Sorry about this one. So this is my 6 to 3, and in this 6 to 3, what I have done just now, I have completed my first winding row. So 1 to 6, there was the connection, 6 minus 3. Now I am at 3 again over there. So now from 3, I have to go now to 8. So you can go back on the table. So now you have 3 to 8 connection over here. So this means that from 3 to 8. So one thing very important, whenever you are doing to it, try to make a small midpoint over there. Even when you are going to do this assignment, this is very important that you have this center point always done, so that whenever you are going to join them together, this is like this, 3 to 8. And then from 8, I have to return back to 5. So now this is going to be the second winding over here. So this is 5, this is 8, something a center point here. And from 8, I'm just showing it like this. So 8 to 5. And then from 5 to 10 now, I'm just going to do it a little faster now so that it does not take much time. So this is going to be 5 to 5, and then from 5 to 10 over there, a little centered, but anyway. And then from 10, I have to go back. If I see the diagram over there, so what I have done just now, I have done this first slot, and then from 10 to 7, I have to return. So if I go back on my diagram, so 10 to 7, and this is the center point over here. So this is my 10, and this is my 7. And then from 7, I have to go to 12, of course, for the same back pitch over here. And then this is going to be 7 to 12. And then from 12, I have to go back to 9 over here. So from 9, this is here. And for 12, I have over here. And then from 12 to 9, I have to go from the 9th part to over here to 14. So 9 is going to be connected with 14 over here. So 9 to 14. So this is something here like this. And so you can see how many coils are being done over there. And then from 14 to 11, this is going to be somewhat here. And 14 to 11. And then from 11, of course, if I go back over there, this is 11 to 16, and then 16 to, so 11 to 16. So this is going to be 11 to 16. And then from 16 to 13, I have it over here. So this is going to be like this. 16 is going to be connected with 13, and then from 13 over here, if I go back on the table, I have the table printed with me, but I'm showing this one for you. So I have 13 plus 5 equal to 18. So now if I have this was 13 to 18, so this is going to be something here. So 13 to 18 over here, and this 13 to 18, and then this one is a little it's managed, I guess. So let me redraw this one, and from this one I have this connection to 18, and then from 18 I have to go back to 15 over here. So this is certainly in the center over here, and from 18 this is connection, and then from again 15 I have to go to 20. So now 15 and 20, certainly this is going to be somewhat here. So this is going to be the 20th slot over there. So now from 20 I have to return back to 17 over here. So this is my 17, like this. And from 17, now the interesting thing, if you go back on the table now, this 17 over here, we have done this one. 17 is going to be connected with 22, and 22 is actually 2. Now I can't show this one 17. 17 is here, 2 is here. So what I'm going to do now, I'm going to leave it something like this, that from 17 I am going to show it over here as this line, and this one is going to be shown over here connected to slot number 2. And here on the other end of this diagram, I'm going to show it over here as slot number 17, like this. So I'm not going to make this diagram a little bad over here, and so this one over here, and then from 2 it is now going to be connected, which means actually 22 is going to be connected back to slot number 19. So what I'm going to again show over here, that this one is going to be connected over here, and this will be shown over here to slot number 19 over here. So slot number 19 over here, and this means that this is actually coming out from here. So this is going to be connected. I'm just showing it over here as slot number 2. So this 2 is going to be connected with 19, and from 19 onward I have to show a coil which is going to go towards, if I go back on your table, this table is telling you from 19 to 4 this is going on. So from then and 4 we have to go to 1, which will be end of this winding. So this will be from 19. I'm again going to show it over here as a arrowhead, and this is going to be from 19 going on towards 4, and from 4 you can see very carefully that this is your 4th one, and this is going to tell you that this is your 19th connection coming on, because this is going to be a completed winding. And from 4 you are going to return back to, if I just rub this one a little, this one. So, and from 4 I am going to show it over here to connection to 1. So I hope you see, then I have all the 20 slots covered. I started from 1 and ended at 1, and this is same exactly just like my winding table over here, that I have started from 1 and ended at 1. So there is no actually 2 ends coming out of the winding. Why? Because this whole of the rotor is going to rotate. So I hope you have got an idea that what is a closed winding over here. Now next thing which I have to do now is this, that I have to now make commutative segments. Now I hope you can see very carefully over there, since this is the front end of your machine over there. So what I am going to do now, I am going to make a straight line over there and another line over here for this one. So now these 2 ends over here. Now what I'm going to do now in this one, this over here is going to be an interconnection with the segment. So this is going to be connected with this one, this is going to be connected with this end over there, this one is going to be connected with this end, this one is going to be connected with this end, this one, and with this one, I'm just going to mark them a little just now after as I complete this diagram. So I have this ends coming out. These yellow colors are also. Now, one thing very important, this one is not going to be connected over there for obvious reason, because this is the same thing as this one. This one over here, this end is the same as this one. We have just repeated over here because this is 2 and this is 19. So same thing. So what I'm going to do, this connection is not going to be there. This one is not going to be there. So what I'm going to do, I'm just going to reduce this one, this size, and this one is just going to be a straight line over there. Now, what does I mean by this one? This is my first segment. This is my second segment. This is my third segment over here. This is my fourth segment. This is my fifth segment over here. Seventh, eighth, and over here this one, and this is this one. So what are these now? This is segment number 1. This is segment number 2. This is segment number 3. Segment number 4. Segment number 5. Segment number 6, 7, 8, 9, and 10. And how they are 10 segments, if you can see very closely, you have 20 slots, and out of those 20 slots you have like 10 segments now coming out. And certainly because there are 10 coils over there, and those 10 coils are telling you. So in practically, when you are actually going to see this commutator segment, just like this diagram as I've shown you over here, this segment over there, over here in this diagram, this will be like slot number 1, segment number 1, 2, 3, 4, 5, 6, 7, 8, and up till 10 over here. So the whole 360 degrees, these are the 10 commutator segments over there, and this commutator segments over there are in this one. Now, how you are going to place the carbon brushes, that's the most important thing over there. So now over here, if I want to have the commutator segment, for this purpose, first of all, I have to make the north pole and the south pole. Now, if I go back on my data, which I tabulated over here, in this data, you can see very carefully that what was your pole pitch. Your pole pitch was equal to 5. What this means that your pole, one pole, either a north or a south, it will be having 5 slots covering. So if there are 20 slots over there, 5 of them will be having a north, the next 5 will be having a south, and the next ones are going to be again north, again south. So how I am going to show them over here on this diagram, now you have, since you have to show the first 5 one, so I am going to show them over here as this one is the north pole over here. So this is my north pole over here, and the next one is my south pole. So over here, this is going to be my south pole over here. Over here like this. So first 5 slots, it was north pole. Second 5 slots is the south pole over there. And you can use any other color. It's totally up to you what color you want to use over there. On this one, I've used this red and blue over there. If you are making assignment over there, certainly you can use some other colors if you want to use it. Otherwise, it's completely okay if you want to use it. So this is my next north pole over there. And secondly, now this is going to be my south pole. So if I mark them now with this, this is my, let me mark it with some, this is my north pole, this is my north pole, and certainly this is my south pole, this is my south pole. Now, what is the advantage of actually marking this one over here? Marking advantage is this, that in front of the north pole, certainly the direction of current in any of these conductors is going to be different than the other pole. So when in front of the north pole over there, the direction of current, if I'm supposing it, now it's totally up to your supposing. If you are working as a motor or a generator, direction of current is dependent upon in which direction you are trying to rotate your rotor. But for this winding example, since any machine can work as a motor or generator, so I'm going to make this north pole in front of this one. Let me use a different intensity. So in front of north pole, I am assuming that the current is actually going inward. over here. So in these 5 conductors, the current is going inward, which means maybe a cross or a dot. And certainly on the south pole, it will be completely opposite to what I have in the north pole over there. So I have this again on the north pole, I have the current direction going in. So you can take it as a cross or a dot, it's totally up to you. In front of the south pole, you have the current again like this. Now what's the advantage, or what I'm actually trying to achieve over here? I'm trying to achieve it that in front of the north pole, all these conductors are having a current direction upward, and in front of the south pole they have a current downward. Here in front of north pole they are upward, here in front of south pole again downward. So now when I'm going to see this one, this diagram, if I see closely now in front of the north pole, is there any end over here? This end over here, this slot 1 and slot number 4, the conductors which are coming, the current is actually leaving from here. This is very important. So from commutator segment number 2, your current is actually entering the windings which is at slot number 1 and slot number 4. So what I mean by this, that there is going to be a carbon brush now. I'm going to represent that carbon brush maybe with the, let me use some dark color over here. So now this second commutator segment, I am going to have a carbon brush over here. Now certainly carbon brushes are black in color, but I'm showing this one with a green over here so that the diagram is a little readable in every sense. So this means that from this side, or in fact let me change this color, let me use a maybe some bright color over here. So I have this one and I have this carbon brush. So this means, and if I am working this machine as a motor, so this means that current is actually entering this machine, carbon brush, and this is the positive carbon brush over there. So current is entering, and you can see very closely that 1 and 4, they both are connected with segment number 2, and here is the first carbon brush over there. Now this is the first carbon brush. If you see the next any two over here, 2 and 6, well, here the current is coming down, and then here the current is coming down, and then from 3 it's going again up. So certainly there is nothing over here. Then if I see 5 and 8, from 8 the current is coming down, from 5 it's going up. So still it's empty. And the next one, if you see 10, from 10 the current is coming down, and from 7 it's also coming down. So this means that the 5th segment over here is also going to have a carbon brush over here, and this carbon brush is going to be negative. For obvious reasons, because I'm talking about a machine in which it's a motor, the current is entering the positive terminal and leaving the negative terminal. Same topology, if I go back on the north pole again over here, you can see at 11 and at 14, here the current is again entering over here. So this means that at segment number 7, I am going to have another carbon brush, and this carbon brush is going to be positive because the current is entering inward. So this will be equal to again a positive carbon brush. Certainly you can show this one over here like this. And then the last one, the last carbon brush, if you see very closely, slot number 17 and 20, here the current is coming downward, here the current is entering, here the current is leaving, here the current is over there. So now your machine is going to have a negative carbon brush over here like this, and these are the 4 carbon brushes of your machine. Now segment number 8, segment number 9, 6, 4, 3, 1, they don't have any carbon brushes. Why? Because this whole of the machine, let me call this one whole, this one including this commutator segment, they are rotating. So these carbon brushes, 4 carbon brushes over here, are going to be providing the power at every instant. This north pole, south pole, north pole, south pole, they will be static. They are static. They are the stationary part of your machine. So the rotor is rotating. So at any given time, the position of carbon brushes is going to be such like this, and this tells you that your winding is going to be having a closed end. You started from 1, you ended at 1. You started from here and you have ended your winding at 1. So this is a closed winding. All the coils are connected in series or parallel combination. We are not just concluded on that one. So over here you are seeing your drawing over here as 1, started from 1, ending at 1, and you have this winding with 4 carbon brushes. Now we still don't know that what are the number of parallel paths in your winding, because if you see very closely in this diagram, the carbon brushes from slot segment number 2 to 5, this has a distance of 3 over here in terms of segments, but from 5 to 7 it's just 2, and then from 7 to 10 again 3, and then from 10 to 2 it's again 2. So there's a little slight symmetry which is not done over here. So it's a light side unsymmetry over here. So maybe we have to now check the last check on the winding, that is how many number of parallel paths are there and how many conductors or coil sides are there inside each parallel path. So for this purpose, the next check you have to do is for the parallel path diagram, which I'm just going to draw in front of you. But before that, now this winding diagram, which is the developed diagram, is complete in front of you. So this means, now I told you in the very start that what was multiplicity. Now if you see very closely, M was equal to 1, that was simplex winding. And if you see very closely, if what is the first coil? Your first coil started from 1 slot and ending at 6 over there. Now if you see, all the dimensions we covered, they were in terms of number of slot. But if you see the first coil is connected with segment numbers, commutative segment number 2 and 3. What is the distance between 2 and 3? It's 1. So 3 minus 2, 1. So this means that the coil span in terms of the distance between the commutative segments is called as the multiplicity. I'm again repeating, the coil span, that is the coil over here, in terms of the commutative segment, which means the starting end and the finishing end of the same coil, their distance is here 1. So here M is equal to 1. So this is a simplex winding over here. If supposingly this ended at 4, then the M would be 2. So this will be a duplex winding. So that will be a completely different case. But here I have M equal to 1 because I have started from 2, ending at 3. So this is a simplex M is equal to 1 winding. This is a lap winding where coils are overlapping each other and M is equal to 1 over here. Now coming on to the very important thing, if I have to, let me copy this diagram and maybe take it on the other one over here, and okay, sorry, on this one. So I have this next page. I have now, the last point of today's lecture is this, that I have to make the parallel path diagram. So how I'm going to make this one, I have just copied this one over here because I want to make a parallel path diagram. And for this purpose, a parallel path diagram, what I'm going to do, I'm going to show a vertical line, and this vertical line is telling me that there is going to be a positive side of this one connected. Now let's zoom in this diagram and see very carefully. I'm going to use this highlighter over there. So you are starting from over here, supposedly the first positive over here, and here you are going to go in slot number 1, and then you are coming down from slot number 6. So here in slot number 1, the current is going up, and then from slot number 6, you coming down. So I am going to show this one as over here. This is going to be, the current is going up, so I'm going to show it with slot number 1 or the coil side number 1. And then from 1, I'm coming down to 6 over here. So this is my 6 coming down. So if I just change this one, this is 6 over there. And then I'm coming down and still there is no negative. So this is no negative over there. So I will again go up, and this is 3. So this means that now this time I have a 3 over here. So this is your 3 over here, the third coil side of the third slot. And then from third, I am again going down and going in 8. So now I have the 8th coming down. So this is my 8th over here. You can see what I am showing over there. This one is the current going up. This is the current going down. And I am showing it as 1, 6, 3, 8. So what are these? These are the coil sides connected over there. Certainly the number of conductors will be much more than that, because the number of turns per coil are different. Now when I am at 8, so you can see now 8 is now connected again. There is nothing, so I will have to again go. So this will be now connected with 5. So this time I'm going to show this one as 5 over here. And after 5 over there, if you see very closely, this is going to, from 5, this is going to go to 10, and at 10 I come at negative. So I started from over here as 1, and I am ending at the 10th over there. So this means that I have my winding. So the current which started from 1 is now connected with let me show this one with a longer line, because I will have many number of parallel paths over there. Like this. So this is my negative side of the machine. So what have happened, I have started from 1, that was the positive carbon brush over here, and after completing tracing the path, what I did, if you see very closely, this is 1 and this is 6, and then from 6 I have to go to 3, from 3 I'm going to 8, from 8 I'm going to 5, and then from 5 I'm going to 10, and this is the path completed. This is the negative, this is the positive over here, and the same I have shown over here in this parallel path. So you can see how many conductors or coil sides, not conductor actually, coil sides are there. 1, 2, 3, 4, 5, 6. So 6 coil sides are there. Now, if I do the very same for all the other current paths, I will do them now very fastly. So now if you are seeing this one over here, what I did, I started from the second commutative segment, which was the positive certainly. So from 2, I went to 1. Now this time I'm going to go towards 4 and then retrace the path over here. So I'm starting from 4, and this will be a current going up. So I'm showing it with 4. And then after 4, it's going in 19. So from here, is going up, and then from 19 I'm coming down. So this is 19. At 19 I reach down over here. Oh, sorry, this one is 19, and at 19 when I come down, it goes in 2. So at 2 it again goes up over there, and then from 2, if you see, I'm going in 17, and then from 17 over here I am actually having the negative. So this means then when I reach this 17 over here, I have to then reach the negative. So my path, this path is only having 4 coil sides. This one was having 6. This one is having 4. So this is a slight discrepancy. And I guess this was evident. Why? Because the carbon brushes were not equally placed over there. You can see this distance, I told 3. This is 2. This is again 3. And the next one is again 2. So that's why the discrepancy was well evident also. But this is confirmed from this parallel path diagram over there. So now what I have started, I have used this first carbon brush. So this was starting from 2, and then I had 2 parallel paths, 1 and 4. 1 I have done over here, 4 I have done over here. The next one now is the second positive carbon brush, because I have positive over here. So now if I complete this one here for the second carbon brush, I have 11. So I will show this one again by a parallel path over here. Current is going up 11, and then from 11 I am coming down to 16 over here, and then from 16 I am again going up to 13 over here, and this 13 over here is then coming down to your 18 over here, and then from 18 I still don't have the negative carbon brush. You have a 15th over here, and then from 15th you have the coming down to 20th over there. So now you have another parallel path with 6 coil sides over there. The last one is actually the positive carbon brush again. The path will be starting from 14. We just did this one path over here, this one, here, this one, and this one, like this, and ending at our negative carbon brush. So this parallel path is done over here. Now I am going to retrace this path, that is actually 14 over there. So if I just do this one, so this one is 14, because now the 14th one is starting, and from 14th I have to go to 9. The 9th slot is having a conductor coming down. From 9 this is going up to 12 over here. So this is 12, and then from 12 there is a 9th portion over there. Let me just confirm it. This is 14 to 9, and from 9 to 12, and then 12 to 7, sorry. So this is 7, and then this is completing again at the negative end over there. So what this means actually, that I have another parallel path now with 4 coil sides. Now this one is very important, that your machine should have equal number of coil sides in each parallel path. Why this is so? Because if your machine is having supposedly a 20 ampere current flowing inside, so what I want, the number of parallel paths over here, this one, the number of parallel paths here which are going to be represented as A here is equal to 4. But what is happening, I have 6 here coil sides, 4 here, 6 here, 4 here. So what does mean, that the resistance of this one is going to be larger as compared to the resistance of this one. So this path is going to have a larger resistance, so the current is going to be on the smaller side. In this path, the current is going to be on the higher side. So machine will have an unsymmetrical torque ripples being produced. So practically the machine is not going to be giving a unidirectional, a constant torque available. So practically this winding is actually not practically possible to make. Why? Because the number of conductors in each parallel path is not constant. So this winding, you can see, right, we started from the winding table, the first of all the calculations, the winding table, the developed diagram. The developed diagram seemed wonderful over there, but over here the number of parallel paths, A is equal to 4, but sadly the number of conductors in each parallel path are not same. So this winding is not practically possible. One thing very important for the lap winding, I am telling you, the number of parallel paths is always given as A equal to MP. M is the multiplicity, as I told you, the distance between the coil sides over there. This one, the coil 1, it started from 1 to 6, and it was connected with 2 and 3. So M was equal to 1. So in my case, M is equal to 1. Number of poles is equal to 4. So A is equal to 4. And this is completely true over here from our parallel path diagram. This diagram is called as the parallel path diagram over here. So this parallel path diagram actually tells us that how many conductors are actually, or coil sides are actually inside each one of the parallel paths. Now here the winding is failed over here because the winding does not have the same number of coil sides in each parallel path. So the number of number of parallel paths in any machine is equal to A equal to MP, the formula employs for the lap winding. And same for the lap winding, the number of carbon brushes. Remember, number of carbon brushes is equal to the number of poles over here in your machine. So this is very much important, that the number of carbon brushes is equal to number of poles. And here in my case, the number of carbon brushes are 4, and that is also the number of poles. So I have this simplex lap winding having M equal to 1, and M equal to 1 suggests that you have the coil sides distance measured in terms of the commutator segment, because this was your M, this one was your 2 started and 3. So this was distance was 2 and 3 for the same loop or coil over there. So this is simplex lap winding. So hopefully in the next lecture I will talk about the duplex wave winding, and I will do maybe a legitimate winding and then complete it. I will not do the whole nomenclature like this one. So this is your developed diagram and your parallel paths diagram, the number of parallel paths, and this all is a lap winding being done. And this example, if you this physical practical motor which I have shown you just today, and also physically in the class also, this one is a lap winding also. So you can see the overlapping very easily over there. You can see the lapping of the coils being done over there, and the lap winding is being used over there. So normally in lap winding, you will see when you will do the next type of winding, which is called as the wave winding, that the number of parallel paths are more. Why? Because A is equal to MP. So when M is there, P is there. So if M is 1, or even maybe P is like 2, or P is like 4 or 6 or something, the number of parallel paths are more. So what this makes, that the lap winding is normally going to have more number of parallel paths. So this means that lap winding is more suited for high current and less voltage. High current and low voltage winding. Why low voltage? Because there are less number of conductors in series over here. So what happens, that there are less voltage but high current, because if this is a generator, supposedly you have like 4 ampere current coming from here, maybe like 3 ampere coming from here, 4 here, 3 here, for obvious reason, because here the number of conductors are different. But still again, this machine is not workable in the longer one over there, so it is going to have a high current yield. Or if it is working as a motor, you will have more paths over there, so it will have more torque as such, but as a less voltage over there. So this is all from the lecture number 9A. Hopefully in lecture 9B, I still not discussed this simplex lap winding. I will do the winding tables and show you the winding over there. But for the assignment, I will be talking about the multiplexed lap winding also, and also the wave winding example. So I hope you have learned something today, and thank you.